things I discovered when I was going through that is if I don't clear it out, I start voicing over the voiceover. And it's like, oh, no, that's not good. All right. So continuous probability distributions. Okay. All right. Okay, any value along a line. Okay, like we talked at 0, 1.1, 0.2, okay, and one of the analogies that some people might use is that if you put a piece of chalk on the board, okay, and if you did all the numbers and you never lifted the chalk, okay, in order to denote all the numbers in the data set, or in order to communicate all the numbers in the data set, that's continuous. If you have to take your hand off and go to 1, and then you have to take your hand off and go to 2, those are called, as you maybe recall from your calculus days, jumps, okay. All right. All right. So, so what we're going to do, we're also going to take, okay, what's the probability for a given number, for a given outcome? All right. But we're also going to talk about a range of outcomes that might be able to occur. Okay. So, if the outcome is 0, okay, or 1, let's just say 2, you can predict a probability that if you put all the numbers in a hat, hold it out, you can predict what the probability is that you're going to get a 2. Okay. Now, if you put that one back in, you got to put it back in, okay, and you pull out another number, and now you want to know what's the probability that the number I select is going to be between 2 and 4. You got a little bit different problem, and that's. All right, and there's what's called the probability density function between two numbers. Okay, it's just basically a good way to think of this is area under the curve. Okay, density is the area under the curve. Okay, and here are some examples. Okay, for this density function. This is when you call this as the area under the curve. That's another way of saying there's a little bit of a Schulteism, so be careful with this because the original guy, and you'll see his name that created this. I'm probably not doing it justice, but this is the area under the curve. All right. And then, so now, what happens if you get a curve that looks like that? What about all these little, kind of jagged edges? And so now, we have a little bit different issue, because how do you get the area for something that looks like this? Or how do you get the probability or the area of under the curve for this? Can't do it, right? Okay, so there's an actual formula that has been created, and there are tables. Good news is there are tables, just like we had with the Poisson tables. Right? And then same way with exponential. How the heck are you going to get the area under the curve for x1 to x2? Hard to do. Okay, so we're going to pick off uniform probability distribution first. All right. All right. So what we have here is a uniform probability density function. Okay. So x, okay, the function of x is 1 over b minus a. Okay. And for anything in between a and b, okay, you're going to get some number that is not 0. Okay. All right, and a is the smallest value and b is the largest value. All right, no big secrets there. Okay. So how do you calculate, okay, the expected value of x? Okay, and the formula is very simple. Okay, and these are just, if you take the distance between two numbers, the expected value is a plus b divided by 2 on a uniform distribution. Because there's no variance in the numbers, it's always the same across. Okay. All right. And now, if you want to get the variance, okay, and this is a dispersion sort of discussion. All right. B minus a over 12. Again, these are formulas that were, I've got some white papers on these if you want to understand, exactly where this one came from particularly. I get asked this one by a lot of the mathematicians, but there's some actual calculations. There's a white paper that's done, and I can share that with you if you're so inclined. All you have to know is that these are the formulas in order to determine the expected value and the variance for X for a uniform distribution. By the way, on the exam, okay, as I think I've talked about this before, is that you're going to get the formulas that you need. I'm not interested in how well you memorize formulas, okay? Any tables that you need, you will get those as well. All right. If you ask me for a formula or a table that I don't think you need, I'm going to push back, okay? But depending on, and I'm probably going to ask you, well, why are you thinking that way, okay? And then based upon your response, I may give you more information. I may give you the formula or more tables. I may not. But generally, these are exams that I've been given 20, 30 times, maybe more than that. Okay, so it's pretty well vetted at this point. Okay. All right. So we got this buffet table. Okay. And the amount of salad taken, okay, is uniformly distributed, okay, between 15 and 15 ounces, 5 and 15 ounces. All right. And so we're going to calculate some probabilities for 5 and 15. Okay. And we're going to use the handy dandy uniform probability distribution, or density function. Okay. X is the salad plate filling weight, okay, because on the x-axis that's the ounces, right? On the and then X is the plate filling weight, and then hold on, okay. And what was the distance between 5 and 15? 10. Yeah. All right. So the expected value of X is A plus B over 2. All right. And if you work that out, it'd be equal to 10. And here's what this guy looks like. All right. So 5 to 15. Okay. Here's your salad. Here's the weight. And so we're going to calculate what's the probability that's going to be between 5 and 15. Okay. Based upon, okay, a uniform probability of 1 over 10. So now let's say you want to do 12 to 15 ounces, okay? And so you take the same thing, okay? It's 0.3, okay? The actual probability is 1 over 10 times 3, because how many numbers are there between 12 and 15? 3, okay? You're still at 1/10 because the overall probability under that curve, okay, was 1 out of 10, okay? All right, let's try another one. This is a little bit different look. All right. Did I put the UC bus in? Oh, look at that. I even modified that thing for you. There's a bus. Okay. Where's the bus come here? Does it come in the circle? Anybody ever taken the bus from here to any place? Yeah, we have. Let's assume that we have a bus, all right, and it says UC on it, and it travels between campuses, and you catch it right out here. I've actually seen people waiting for the bus, so, well, they're waiting for something, I don't know. Maybe they're waiting for the pizza guy. Anyway, but let's assume that they're waiting for the bus, all right, and the bus arrives, okay, every 30 minutes between 6 and 11, and so you want to understand what's the probability, okay, that the person, so first you're going to draw a graph, okay? And they wait uniformly between 0 and 30 minutes. So you're going to graph it out first, show the area on the curve, that's 1.0, and then we'll calculate how long it actually takes, or how long a person will typically have to wait on that bus, right? And that's the exercise. Please work amongst yourselves. If you've never participated in any group discussion or team discussion, we're going to be fine. We'll slow down on these chapters if we need to. Okay, so don't worry if it's not looking like it's going to exactly work out. Okay. All right. Okay, so you got that down. Now, and I'm going to skip through some of these next slides pretty quickly, okay? Because now we're going to go for normal approximations, okay? And some of the discussion there is that the larger that number becomes, okay, it gets harder to do with a calculator. And especially, I guarantee you that as soon as you start moving toward a normal distribution and a binomial nature, the binomial nature between x1 and x2, or what we said before was between 5 and 10 as an example, or 5 and 25, okay? All right. All right. And so you can begin moving toward some probability type of discussion, n times p. We've talked about that before, okay? All right. Yes, okay. We talked about that. So what's the probability that the value is going to take on some number between x1 and x2? Okay. That's what we're talking about here. Okay. And we're going to do it with using the area under the curve just like we did before. And you're going to hear this term. This is going to be hopefully drilled into you by the time you get done, certainly with BANA, you're going to get BANA 2. You're going to get tired of hearing about the normal probability distribution curve. I mean, it's just the basis for all things associated with probability in somewhat the real world. Okay, so I mean, it can be used for anything. I mean, test scores, scientific measures, rainfall amounts. Okay, and you can just say, okay, I've taken a sample of everything that's happened in the past, and I can tell you, okay, this is kind of what the Farmer's Almanac does. Anybody familiar with the Farmer's Almanac? Okay, that predicts what the weather is going to look like. It kind of goes by that, right? It goes by what are the probabilities that this is going to occur. And then the woolly words comes out, and it's not woolly enough, and suddenly the Farmer's Almanac is wrong. So take that for what it's worth, all right? And then the weatherman, sometimes he's wrong too. Hey, it's not going to rain today, and you look outside, and it's like, what? It's pouring down rain. Okay. Any French students here? Any French students? Okay. But I'm going to talk freely again. Abraham de Montvilliers. Okay, he was a French mathematician, and he sat down and he noodled through this thing. What caused him to think about this situation? I have no idea. But the good news is he thought about it. He figured it out, and he derived this normal distribution type of function. Okay. So you got a handy dandy formula that we'll be using. Okay. Now there's some important points here. There's some very, very important points here on a normal distribution curve. You have symmetry. Okay. Okay. And that basically means that it's a mirror. Okay. You put the mean down the middle, or not the mean. You put the mean at the apex of the curve. Okay. And some of you on the quiz didn't put the mean at the apex of the curve, but it's going to become even more important now. All right. And there is no skewing. Okay. There's no distortion. And in fact, the kurtosis, the peakiness that we talked about before, is also very normal. And we're going to have a family, if you will, of these different distributions. Okay. Okay. So the skew is 0. You're totally symmetrical. Okay. Engineers love symmetry, right? Okay. Now, the other interesting thing here is when you get into sampling, there's another term called asymptotic, which means these lines never actually really meet. Okay. But we'll save that for that excitement for the next chapter. All right, so let's just let this thing build a little bit. All right. All right, so just like we talked before, you have the mean, okay? All right, right in the middle. It hits the top. Now, mu is for the population. If that were x bar, what would that denote? Sample, that's right, exactly. But we're talking mostly about population at this point, okay? We have a standard deviation, which we've calculated a few times, okay? I'm not going to make you calculate. I'm going to give you the standard deviation, and you would know that if the standard deviation were 3 and the mean were 6, you would know to go +3 and -3 from 6, and you got your plus or minus 1 standard deviation, correct? As far as actual values go. Okay. All right. The other thing that's important when you hit the mean, okay, or when you hit normalcy, is that the median and the mode and the mean are all one value. Remember how you drew earlier on? Okay, you said, okay, they're skewing because the mean and the mode, the relative relationship between the mean and the median. Okay, all right. So now there is no relative difference between the median, and mode. They're all the same, and the mean is always the highest point. Okay. And here's let me do a couple more characteristics, and then I'm gonna have to shut this out. Okay. And the mean can be a numerical value, any number. Okay, positive, negative, 0, a fraction. Okay, any number, and that's why we're into the continuous chapter. Okay. Okay, so you can see here along this axis, if you want to take the situation before here was 0 minutes, you know, maybe a bus couldn't show negative 10 minutes, but you can get negative temperatures. Okay. And I think we're doing well here. All right, now, the other thing, the last piece I want to mention here is this is the peakiness. You're going to hear this as kurtosis, K-U-R-T-O-S-I-S. Nobody really talks about kurtosis, but if you're at a pub or at a social outing and somebody starts talking about kurtosis, you can join in the conversation. All right. And basically what that means is you're getting more peakiness, which means that the standard deviation is tighter about the mean. There's not as much dispersion. Okay? I'm going to stop it.